So, welcome to the course UEC 001. In this module, we will discuss various specification of operational amplifier. So, starting with gain bandwidth. Gain bandwidth. So, for this gain bandwidth, we have to draw a frequency response. So, in this frequency response plot, on vertical axis, we are taking gain and we are taking gain in a unit decibel, and on this x-axis we are taking frequency in terms of hertz, and specifically this will be in logarithmic scale. So this is on logarithmic scale, and the frequency response is somewhere like this. This is the frequency response of operation amplifier, where the maximal value is termed as AVD, where this term AVD is my AVD is termed as large signal. This is my large signal differential voltage gain. Large signal differential voltage gain, or in some literature it is written as open loop voltage gain. So this is a specification given in the literature of the IC or user manual. So we have to find the bandwidth. So we have to find a point of level 0.07 times AVD. So the frequency when I will have value of gain 0.707 times of AVD. So this is termed as my FC, where FC is the cut off frequency. FC is my cut off frequency, and it is calculated when gain attains a value 0.707 of its maximal value, that is AVD. Okay, so that is my frequency FC, and you can check at this particular point. I am referring, this is my F1. So F1 is the frequency, F1 is the frequency at which gain is unity. F1 is the frequency at which gain is unity, and this is very interesting parameter. In fact, you can see that on this scale, on vertical scale, we have taken gain in decibel, and if you can recall, we have discussed on previous lecture, that is my gain AVD will term as 20 log base 10 output voltage upon input voltage. So you can check at this point, I have taken if this gain is unity, if ratio V naught upon V in equals to unity, then on logarithmic scale the value of AVD will be equals to 0, because log unity is 0. So I am having interesting parameter F1 is the frequency at which gain is unity, or we can define this in terms of bandwidth. So like I am having a parameter B1. B1 is the bandwidth when differential gain differential gain is unity. So I'm driving a relation V1 equals to AVD multiplied by frequency Fc. So sometimes this F1 is also known as unity. This F1 is also termed as unity gain bandwidth product. Unity gain bandwidth product. This is also known as unity gain bandwidth product. Now, for better understanding, let us take some point. I am marking a reference point, and suppose at this reference point I am having a value a dash, that is of my gain, and at this particular term suppose my frequency is f dash. So this is my magnitude of frequency and gain. Okay, so at this particular point I am referring, that is my fp, the product of frequency and gain, and this will be termed as simply a dash into f dash. So my gain bandwidth product at certain point p can be estimated as the product of their respective gain and the frequency. So fp is my gain bandwidth product. So fp is my gain bandwidth product. This is very interesting specification of operation amplifier, and let us discuss one example. Let us discuss one example uh, for the standard IC mu A741C. This is commercially available IC, and let us find the gain bandwidth product. Gain bandwidth product for mu A741C. So the typical value of B1, the typical value of B1 for this IC is 1 megahertz. That is 1 into 10 raised to the power 6 hertz. This is the standard value of B1 for IC 741, and the value of AVD, the value of differential voltage 200 volt per millivolt. So it is 200 multiplied by 10 raised to power 3, because in numerator it will be 10 raised to power 3. So my AVD becomes 200 into 3. That means this is 2 into 10 raised to power 5. Okay, this is my open loop voltage gain. Now let us calculate the value of F1. Therefore my FC, we have studied the relation F1 equals to AVD multiplied by FC. FC will be equals to F1 divided by AVD. F1 is given as 1 into 10 raised to power 6, and AVD is 2 into 10 raised to power 5. So it is simply 10 divided by 2. So my cutoff frequency Fc is 5 hertz only, and this is one of major drawback. So op-amp cannot be used in open loop configuration as its cutoff frequency is very low. That is, Fc equals to 5 Hz for IC mu A741C. So this is the important limitation. This is the important limitation of IC mu A741C, because we cannot change the value of gain AVD, which is 2 into 10 raised to the power 5. So we have to do some mechanism. We have to find the alternative, and the alternative is the alternative of this problem is to use op amp in closed loop configuration. In closed loop configuration. So with this, we will reduce the value of voltage gain. We will reduce the value of voltage gain so that the value of cutoff frequency can be increased as the value of F1 is constant. The value of F1 is constant for IC mu A74C. This value is constant. So this is the alternative solution we are having. We can use the closed loop configuration. So in this module, we will discuss in detail the closed loop configuration. But before that, let us discuss the typical value of some important characteristics of IC mu A74. Okay, so let us write a term: input offset voltage. So my input offset voltage, and these all we are talking for IC mu A741C. We are talking in relation to this IC. And typical value of input offset voltage, so one can represent it VIO. V stands for voltage, I stands for input, and O is standing for offset. And the typical range for this is from 1 millivolt to 6 millivolt. The maximum variation in input offset voltage will be at 6 millivolt. The next parameter over here is input offset current. Input offset current, and the representation of input offset current is I naught. So again, the notation is clearly indicating the purpose. I stands for current here. This is small I indicating input, and O is offset. And the typical range for IC mu is 74 from 20 nano ampere to 200 nano ampere. The next component is my input bias current. Input bias current, and the input bias current is notation is IIB. So again, notation is representing the purpose. I stands for current, small I is input, and small b is indicating the bias current. If you can recall, in the block diagram we have shown that the first block is dual input balanced output differential amplifier. So differential amplifier means we are giving this particular current to the one of the base of the transistor, and its typical range is from 80 nano ampere to 500 nano ampere. My next parameter is, we have just discussed, it is large signal differential voltage gain. Notation, its standard notation is AVD. It is also termed as open loop voltage gain. It is also termed as open loop voltage gain, and its typical value is 200 volts per millivolt at a input. That means it is 2 into 10 raised to power 5. Now my next parameter in this is F1, gain bandwidth product. Gain bandwidth product. We have just discussed this term, gain bandwidth product F1. The typical value for this is 1 megahertz, or it is 1 into 10 raised to the power 6 hertz. Next parameter is input resistance. And the value of input resistance notation is in fact Ri. Typical value for this IC is 2 mega ohm. Next component is output resistance. Next component is output resistance, and a typical value of output resistance for this IC is 75 ohms. If you can recall, we have discussed two more components, CMRR and CMRR, common mode rejection ratio for IC mu A741C is 90 decibel, and taking one more component, slew rate, which will give us the information of rate of change of output as a function of input, and its typical value is 0.5 volts per microsecond. So this is the drawback. For this IC, slew rate is poor. However, if you can recall, we have discussed that the value of slew rate should be infinite for the ideal case. So these are few characteristics for practical operation amplifier we have discussed, and these are the typical values for IC mu A741C. The first case, let us discuss the first case over here, inverting mode of operation. Inverting mode of operation. So let us see in closed loop format the functionality of operation amplifier in inverting mode. So I am drawing the circuit diagram first so that we can easily understand the working of operation amplifier in this mode. I am having a series resistance using the standard notations. Series resistance is R1, a feedback resistance. This is a feedback resistance, and in general the notation of feedback resistance is RF, giving input signal to the inverting amplifier. So you can check, I am giving V in input signal to the inverting amplifier and making non-inverting terminal to ground directly. Making non-inverting terminal to ground. This is my plus VC supply. This is my minus VE supply. We require some load resistance also, across which we will measure my output voltage V0. So this is the configuration. Let me write explicitly the typical values. This is a terminal. Suppose V1 is the voltage. This is non-inverting terminal. I am saying that's terminal V2, and differential voltage across these two terminal should be VD. So explicitly writing, this is my feedback resistance. This is my feedback resistance. This is my series resistance. Load resistance across which we are measuring the output. This is my load resistance. I am measuring output across here. Okay, and suppose current flowing through resistance R1 is current I1. Current flowing through resistance feedback is current IF. Okay, and current flowing through here is current IB1 and current IB2. So you can check, we have applied input signal to the inverting terminal. Okay, so let me draw their input and output waveforms also, so that you can better understand the concept of inverting mode of operation. I'm considering this is my input, this is my input of some magnitude. So my corresponding output over here is, it should be a phase shifted and amplified version of the input. So this is my output V naught, and you can check there is a phase difference between input and output, and it is of 180-degree, and this is due to inverting mode of operation. So we will verify mathematically how it will appear. So applying KCL at node V1, apply apply KCL at node V1. So what is KCL? Algebraic summation of all current should be equals to 0 to a particular node. That means current I1 will be equals to current IB1 plus current IF. If I am assuming my op amp is ideal, if I'm assuming my op amp is ideal, input resistance Ri will be infinite ohm. Due to this, the value of IB1 will be equals to 0. So I am having equation current I1 equals to IF on, and this is for ideal operational amplifier. This is for the ideal operational amplifier case. Now, what is the value of I1? It is V in minus V1 divided by resistance R1. So, V in minus V1 divided by resistance R1, and similarly IF equals to V1 minus output voltage V0, that is the potential difference across feedback resistance RF simple. Okay, and now in this term, use virtual ground concept. Now use virtual ground concept. And what it says, virtual ground concept says that V1 will be equivalent to V2. And from this diagram, you can check non-inverting terminal is directly connected to ground. That means V2 is 0. So V2 equals to 0. Therefore, V1 seems to be virtually grounded, and it will also be equivalent to 0. So terminal V1 is termed as virtually grounded terminal. So we will use over here virtual ground concept. My relation is V in upon R1 equals to minus V naught upon RF. And from this relation we can solve, that is my voltage gain. So this is my closed loop voltage gain. In case of inverting mode of operation, AV, which is V naught upon V in, which is equals to minus RF upon R1. So we can check, we can control the feed closed loop voltage gain by connecting external resistance. Here RF we have already seen. I can better understand. RF is my feedback resistance and R1 is my series resistance. So we can control the gain of operation amplifier using external hardware RF and R1. And you can check this minus sign is indicating a phase shift of 180 degrees. Okay, so this is the case of inverting mode of operation. Okay, now let us discuss the second function, non-inverting non-inverting mode of operation. Non-inverting mode of operation. As the name suggests, non-inverting mode, that means we have to apply signal to the non-inverting terminal. Again, let us see first the circuit diagram. So now you are having basic idea of circuit diagram from inverting mode of amplifier. Now I am drawing the feedback resistance, need a load resistance across which we need to find the output voltage V naught. This is my load resistance RL. This is my feedback resistance RF, plus VC supply minus VE supply. Inverting terminal. Inverting terminal has to be grounded. Series resistance R1. And now I am giving input to the non-inverting terminal. This is my V and non-inverting terminal. For better understanding, I am referring, this is my V1, this is my V2. So obviously VD will be the difference of these two. Again I am saying that current I1 is flowing here, current IF is flowing here, and to these two base terminals current IV1 and IV2 is flowing. So I am not writing their details. This is clear cut. My series resistance, feedback resistance, load resistance across which we will take the output, and input we have applied to the non-inverting terminal. So first let us check their input and output waveform for better understanding. If this is my input signal V in of some magnitude, then I will have the output amplified version of my input. This is the amplified version V naught. Interesting part over here is both are in same phase. So phi will be here 0 degree. That means there is no phase shift between input and output. KCL at node V1, the same procedure which we have followed for inverting mode of operation. Now I am directly writing current I1 equals to current IB1 plus current IF. Again, assuming the case if my op amp is ideal, so current IB1 will be equals to 0, and I am having directly I1 equals to IF. That is, current flowing through the series resistance will be equivalent to current flowing through feedback resistance R, and their value is, now it is 0 minus V1 upon R1 will be equals to V1 minus V naught divided by RF. Or I am just doing a bit manipulation. V naught upon RF will be equals to now V1 times 1 upon Rf plus 1 upon R1. Now again we have to use virtual ground concept. We have to use virtual ground concept, that is the two terminal voltages should be equal, V1 equals to V2, but now here V2 equals to Vin, so these two should be equals to, therefore voltage V1 will be equals to Vin. So virtual ground is saying that even though we have applied the voltage across V2 input voltage, V1 will also be take similar, so that Vd will be equals to 0, making voltage gain amplification in open loop configuration to the 0, sorry, infinite. So V naught upon Rf will be equals to Vin times 1 upon Rf plus 1 upon R1. And finally, from this, we can derive the relation of voltage gain for non-inverting configuration, that is AV, and this will be equals to now AV equals to output voltage upon input voltage, and will be equals to 1 plus Rf upon R1. So this is the voltage gain for non-inverting mode of operation, and this is my 1 plus Rf upon R. And you can see that there is no sign means positive sign, so no sign means there is no phase shift between input and output. So this is the second case, non-inverting mode of operation. Now let us check the third case, and third case is unity gain unity gain amplifier. Let us find unity gain amplifier, the third one. So as the name suggesting, unity gain amplifier, that means its voltage gain will be equals to unity. We need a circuit which should have AV equals to 1. If you can recall, for non-inverting case, we have just seen that the value of AV will be equals to 1 plus RF upon R1. If somehow we are in a position to make this RF equals to 0 and this R1 equals to infinite, so what we will have, AV equals to 1. That means if somehow we can do these two things, we will be in a position to have AV equals to 1. So how we can achieve this? RF will be 0 means we will replace this RF by short circuit. If we replace RF by short circuit, and this infinite means replace this R1 by open circuit. So now I am directly drawing the circuit by using these two. This is my optimum. Definitely I will need a load resistance to find the output voltage V0. I am saying that this is my RL. Okay, so you can check, I have replaced RF by 0 ohms. No series resistance means open circuit, and whatever be the input I am having, I am applying that input to the non-inverting input signal to the non-inverting terminal, that is my Vin, inverting non-inverting terminal, and there is the external supply plus Vc and minus Ve. So this is my unity gain amplifier, and you can see that we have given input signal to the non-inverting terminal Inverting terminal is feedback and connected to the output.